Okay, well, welcome back to the second part of the first tandem of the day. I'm very delighted to introduce to you our speaker for this part of the tandem. It's Olival Freire Jr. I'm not sure if my mic is working. From the Universidade Federal de Bahia, Brazil. He's a full professor of physics and the history of physics there. His main subject of interest in physics as well as history of physics is quantum physics. And he has many outstanding contributions there, mostly well known probably for his book, The Quantum Dissidents, Rebuilding the Foundations of Quantum Mechanics from 1950 to 1990. And I'm sure he will tell us much more about this himself in his talk. So let's welcome Professor Olival Freire from Universidade Bahia.
Okay, good morning. First, I would like to thank you very much to Flavia and Bernadette for organizing this interesting and challenging conference and inviting me for this presentation. Second, I want to say that it's an honor to chair this tandem walk with Dan Greenberg because he's one of the subjects of the history I intend to present. Third, as you can see from the title of my talk, I will speak about a kind of a prehistory of quantum information, in the sense that quantum information emerges as a full field of research in the early 90s. So I want to cover the conditions previous to the emergence of quantum foundations. Thus, in a certain sense, it will be also a prehistory of some of the questions Dan Greenberg presented here, because indeed the GHZ theorem appeared in the late 80s. So the history of the GHZ theorem begins when my history ends. And third, I would say that my talk will overlap with David Kaiser's presentation yesterday in many aspects. I should say that I reflected yesterday if I should change or not my talk, but in the end, I decided to keep as I had prepared. Mainly because this overlap is an expression of the things I learned with David in the last 15 years. We have been interacting and discussing about this subject. Okay. So, as you well know, research on the foundations of quantum mechanics entered the 21st century as a blossom field, a field which is considered good physics, normal physics, mainstream physics, and but furthermore, it is related to the promise of applications in the field of quantum information. That's the reason, for instance, that in 2010 we had this prestigious Wolf Prize in Physics awarded to Clauser, Alan Speck, and Anton Zeiling for their contribution related to experiments on Bell's theorem, on Bell's tests of Bell's inequalities, or extensions of these inequalities, which includes the GHZ theorem as one of these extensions. So from my point of view, the history of Bell's theorem and the history of quantum entanglement encapsulates the historical changes undergone by research on the possibility of completing or enlarging quantum mechanics through the introduction of additional hidden variables. In the end of the day, our conclusion is that if hidden variables is to be introduced in quantum mechanics, it cannot be the kind of hidden variables which are local hidden variables. But this is the conclusion in the end of the history. So from my point of view, there is a line from the early discussions about introducing hidden variables to the conclusion we had in the end of these histories. However, it was not always that foundations of quantum mechanics and the issues such as this about hidden variables were positively considered. Indeed, this subject once occupied a very marginal position, a philosophical issue beyond the pale of scientific research. We have seen yesterday some of this through David's talk, but I can recall that in the early 50s, Isidore Rabi said things like that David Bohm's reinterpretation of quantum mechanics was analogous to the angels which people introduced in the Middle Ages to explain things. If you take the late 50s, you have a little better consideration, but Messier said things like that. Hidden variables pertain to the philosophy of science rather than to the domain of physical science proper. In the mid-60s, I will show later, Bell's work was considered by Rosenfeld a waste of talent. And even in the early 70s, some physicists still wonder whether the experimental research with Bell's theorem was real physics. Considering foundational issues worth of investigation is a kind of a renaissance in the history of quantum mechanics, because it's true that in the inception of quantum mechanics, there were heated debates among the founding fathers of the discipline. Then these debates disappeared, and then they came again. So my historical question, or the question I think that requires a historical explanation, is that what were the factors which brought foundations of quantum mechanics from the margins to the mainstream of physics? That's the title of my talk. From my point of view, these factors were diversified. They were not unique. They did not act, these factors were not effective all on the same time, on the same place. If you want to write this history, you needed to disentangle these different kinds of factors. In this short talk, I will not try to present a whole history of this in details. I just want to suggest a kind of a cartography of these factors. In fact, a list of these factors without considering their development through time. So this is the list of factors I want to emphasize, and I will just take a few ones for our consideration. Let us begin by the conceptual issues. So this is my first point I want to emphasize. We need to recognize, now it's easy to acknowledge this, that there were important conceptual issues in the when quantum mechanics was created, and some of these conceptual issues were not dealt properly at the time. So one of the question, it was exactly this question. Sometimes it appears as the title of hidden variables, at the other times about which the title of if quantum mechanics is complete or not. Many times this was related to determinism, other times not. But this was an important question in the inception of quantum mechanics. From my point of view, it was so important that even if Louis de Broglie abandoned this question in 1927, it was not by chance that in the 30s, von Neumann, when he wrote his monumental work about the mathematical foundations of quantum mechanics, he dedicated a section to present his proof against the existence of hidden variables compatible with quantum mechanics. So it was not a minor question in the inception of quantum mechanics. As you know, the question he appeared in the debates between Einstein and Bohr in 1935. I don't want to enter into details. And finally, it came more clear in the work by Bell's theorem in 1965. And this is the solution. Bell was able to identify certain assumptions in Einstein's reason. The first one, realism, the second one, locality, and he was able to translate these conceptual, these philosophical assumptions in a kind of a mathematical expression, the first Bell's inequality, and quantum mechanics does not satisfy these inequalities. So this is Bell's theorem. Quantum mechanics may, in certain cases, violate Bell's inequality. It's not in all cases, because here you have hidden variables, quantum mechanics. You have in some parts of the graphs, you have divergence, but it is not in all positions. Now, since the early 60s, since the early 70s, this was brought to the lab bench. Daniel Greenberg recalled us that Michael Horn just passed away recently. I didn't know that, and the role of this CHSH paper. It was this is a wonderful chapter in this history because Michael Horn was a doctoral student of Abner Shimon. Klaus had already a doctoral training, and it's also a nice history because this had everything to become a competition between Klaus and Shimon, and then inspired by Wigner, Shimon decided to make a phone call to Klaus, and instead of competing who was the first to understand the Bell theorem and their experimental implications, they decided to collaborate, and that's the origin of this wonderful paper. Now, these experiments has a full history. I don't want to enter in details here. Daniel Greenberg called our attention for the role played by the new source of entangled photons. It was used by Yann-Hashi, Mandel, Deininger, Nicolas Gisin, and the others. And the full conclusion of this is that entanglement was considered maybe after Alain Spert experiments, or maybe after Richard Freire experiment in 1976 as a physical phenomenon. And then you had this last kind of experiments, like the experiments in the Canary Island, and the very recent one when you are using cosmological data to have a kind of random numbers to try to close indeed closing at a certain limit the loopholes in this kind of experiments. So before going to the measurement problem, the second conceptual issue, I want to emphasize this. The possibility of completing quantum mechanics was a kind of analogy with the relationship between classical mechanics and statistical mechanics in the 19th century. So it was very common, this idea. What is the theory behind quantum mechanics, which is for classical mechanics as quantum mechanics is for statistical mechanics. So this was a conceptual issue. This was not a minor issue. And the existence of this wonderful history of more than half a century of theoretical developments and wonderful experimental developments just show us how important these conceptual issues were. Now, the second conceptual issue, the measurement problem. We were discussing in the break when the measurement became a problem. This is a nice question because from my point of view, this was not understood so in the inception of quantum mechanics. From my point of view, you had in the 1930s two solutions. The solution by Niels Bohr, that you needed to use plain language, so you need to use concepts from classical physics in order to communicate the result of experiments. And you had the other solution by John von Neumann, who identified two different evolutions of the quantum states. But you cannot find in the texts a huge debate about the quantum measurement, and you cannot find the word quantum measurement problem. Indeed, as far as I know, there was a debate between Bohr and von Neumann in 1939, so on the eve of the Second World War, where it's clear from the proceedings of this conference in Warsaw that they had a difference. Bohr was not satisfied with von Neumann's presentation, but it was after the World War II that the problem became more clear. From my point of view, the attempts to touch what we call quantum measurement problem began in the 50s because Bohr's solution was too philosophical to be accepted by physicists, and the von Neumann's solution was too mathematical to be accepted by the physicists. So from my point of view, the two solutions had some weakness. But it was indeed in the 60s that the quantum measurement problem indeed emerged as a problem by the hands of Eugene Wigner. I think that he was the main player in this history. As far as I could check, the first time the expression quantum measurement problem appeared in print, it was in Wigner's 1963 paper, exactly with the title Quantum Measurement Problem.
1949, a paper by Jordan.
I didn't know. Wonderful. Good.
And I found that because I read yours.
Good.
And I worked harder.
Excellent. But it's fantastic that during the 50s when people...
There wasn't much mentioned.
Yes.
But I can show you the Jordan.
Yeah, wonderful. Now, this problem was very important in the 60s due to a kind of a sociological problem, if you may see, because this conceptual problem became part of a very strong dispute between the Italian physicist Danner, Log, and Prosper, who presented a physical solution for the measurement problem, the thermodynamical amplification approach. This solution was supported by Leon Rosenfeld, who in the 60s was considered a kind of the outspoken person to represent Bohr's point of view, who was no longer alive. And this solution was criticized by other physicists, Ebner Shimon, Michael Ian Naz, who were students of Wigner. And Wigner entered into the debate. And it's in the late 60s that the idea of the existence of a Copenhagen school and the Princeton school appeared among physicists, or the idea of a clash between Wigner and the Italians. So this was I could talk a little bit about the measurement problem, but I want just to say two things. Everett relative states approach, even if it is not usually seen as a solution for the measurement problem, but one of the strong motivations for Everett, it was that he did not accept the von Neumann's presentation of two evolutions for the quantum states. So in a certain sense, we can say that Everett's work was motivated by the existence of the quantum measurement problem through the solution of von Neumann's, which Everett did not accept. And the other comment, I would say that there is another problem related to the measurement problem, but not exactly identical to the measurement problem, which is the transition from the quantum description of a system to the classical description of a system. Okay, I will not speak about the less of this approach, but I want to speak about what emerged as the coherence effect was, in a certain sense, related to the awareness of the problem that you have a problem as how can a classical description appear if you take as point of the departure the quantum description. So this was the work by Teil, a kind of forerunner in this work. By the way, he just passed away last year, and Leggett and Caldeira and Zurich and the others. Now, here, this iconic drawing in the Zurich paper in Physics Today. Now, we had the other conceptual issue from my point of view, which is the connection between quantum and gravity. To say this today, it's nothing new. It's not by chance that this series of talks, one is dedicated to quantum foundations and the other dedicated to gravitation, quantum gravitation. But what I want to emphasize is that this connection, or the problems related to connect quantum mechanics to gravitation, was also a problem considered by a problem early, at least early on, like 1960s. So this is the paper by Brice de Witt in 1967. When you can see that it's a very important paper, part of three papers where appeared what we now call the de Witt-Wheeler equation, but indeed this paper is just by de Witt. And for the first time, you had this kind of thing. You had a paper discussing quantum theory of gravity. So it's not working, but you can see. So he discussed what he saw as an insufficiency of the Copenhagen view, and he suggested, or he had rediscovered the Everett interpretation, or the Everett approach as a possible solution for the quantum treatment of gravitation. So it was a kind of third conceptual issue, which are, from my point of view, on the roots of the emergence of the research on quantum foundations. It is not by chance that Brice de Witt, after this work, this is very important work for his research, he became a vocal advocate of Everett's interpretation. He rediscovered the original dissertation. He used the word, many words, and he had an important participation. I will talk a little bit later. Now, I want to say that the other roots of interest in quantum foundations, these are the philosophical implications and philosophical commitments. This is very important for the session we are discussing. I don't want to enter into details, but what I want to say is that even if many physicists dislike the blend of physics with philosophy and preach they shut up and calculate, the fact is that philosophical implications, philosophical assumptions were instrumental in the history of the research of quantum foundations. From my point of view, not only the realistic point of view, because it's easy to say that Bohm, Bell, Einstein were realistic, then realism played a positive role in fostering the debate on quantum mechanics. But I would say that also an instrumentalist view also played their role. I always want to recall a paper a little bit forgotten by the French physicist Paul Langevin, who wrote exactly about how realism and instrumentalism have been in different circumstances driving force to develop quantum mechanics. This paper was written in the late 50s or early 30s, so he was thinking about Einstein and Heisenberg's contributions, and this paper for me is very important because Langevin was a true committed realist, but he acknowledged the role of both parts, or both kinds of philosophical commitment had played in the development of physical theory. And I like, among the main example of motivating or at least philosophical commitments which had which played a role in the development of quantum foundations, I like to cite Roy Glauber, the pioneer of quantum optics. He said once, "I don't know anything about photons, but I know one when I see one. And sometimes disappears when I detect one." This,
he doesn't know anything about what?
I don't know anything about photons, but I know one when I see one. So this is typically an instrumentalist view, but this was important in his way to quantum optics. Now, we also had new techniques. I just want to say, David, remember that even an experiment is not enough to convince the physics community of the importance of some field. And I had through almost maybe 10 to 12 years a debate with John Bromberg, a great historian of physics, because we were working on similar fields, but she emphasized the idea, the role of instrumentation, the role of applications, and our discussion was always, okay, new instrumentations, like this beautiful picture of IBM. So manipulation, single photons, down conversion, manipulation of single atoms, electrons and photons and so on. This was very important, no doubt. But this played a role from the mid-80s on. You cannot see this playing a very important role before. If you see, for instance, not Alain Aspect experiment, because Alain Aspect had at least the tuning laser to excite the atoms, to get the pair of correlated photons. But if you take the first experiments that you show the picture, the technique was the technique of the 50s. So even the pictures, if you compare this picture with the recent pictures, you can make an experiment in quantum optics on this table. And Klaus took 200 hours to take numbers from his experiments. So technical improvements played a role, but a role which was important later from the 80s on. And from the 80s on, it was a very important, it played a very important role. Now, I'm going to skip some of my parts, but I want to emphasize now the idea that as important as these questions I presented may be considered now, I would say that these foundational issues could have lain dormant for a long time if not for the role played by the physicists who worked on them. I may give you an example of an inactive issue in the history of physics, which was the nature of inertia, the nature between the relationship between the gravitational and inertial masses in Newton's times. It took centuries for the question be emphasized by Ernst Mach and later by Einstein. So it is not because you have an important conceptual issue that this question will be considered by a physics, a scientific community. You need to have people who want to say, here we have good science to be done. And that's the moment I want to introduce what I call the quantum dissidents. So the quantum dissidents for me are the physicists who worked on this field in a time where this field was not so well considered as in the late maybe 20 years. Now, I use this expression, dissidents, because I think that so it's a question, why I call them dissidents? Were they against Copenhagen interpretation? Were they against Bohr's interpretation? Most of them, yes, not all of them. The most important for me is that they challenged the common wisdom or the received view at that time that foundational issues were already solved and not worth pursuing. So this idea I took from an early paper by Bell and Nuremberg in 1966 when they wrote this kind of thing. The typical physicist feels that foundational issues have long been answered and that he will fully understand just how, if ever he can spare 20 minutes to think about it. So who are these quantum dissidents? I brought here a kind of family portrait of the quantum dissidents. That's why you are here, going back. You have here the full GHZ. So I like this picture for a number of reasons. One of the reasons that this happened in 1990. So it was before the explosion of quantum information, when quantum foundations were subject for a small number of physicists around the world. So the second is that because Bell is still alive, and we have a number of other people I like very much because we have here Abner Shimon in the end, a person I like it very much, but also for the topic of today, the full GHZ theorem in this conference, this Helmholtz conference. Horn, oh la la, on the left, Darling on above, and you are not so tall. You can identify where you are. Let me see if you, oh, but you can see. Okay, let me say a few things about the quantum dissidents. So, these quantum dissidents, they needed to face prejudice against the hidden variable issue and against the research on foundations of quantum mechanics. Okay, so just to have no doubt where you are here. So here you have the G8Z theorem. Okay, so the kind of prejudice they faced. John Bell was familiar with this kind of prejudice because so before, sorry. I took this picture from the 1990s, but the quantum dissidents for me include, obviously, Bohm, Everett, Wigner, people who were over there. Other people, less known people, like Mario Bunge, like Klaus Tausk, and younger people like Nicolas Gizan and the others. What they have in common is that they had this attitude to see, here we have good physics to be done. That's the shared view. Now, about the prejudice, I said you that Bell faced this problem early on, 1966. He was already a very respected physicist, but he had just published these two papers criticizing von Neumann's proof and presenting his theorem. And he received this letter from Leon Rosenfeld. I need not tell you that I regard your hunting hidden parameter as a waste of your talent. So this was the kind of bias that Bell was familiar. So it was not by chance that the first time Alain Aspect went to discuss 1976, he went to discuss his experiments, the experiments which were published in 1981-82. To discuss these experiments with Bell, the first question Bell asked Aspect was not about the content of the experiment. The first question was, do you have a permanent job? The fact is that Aspect had a permanent job at the École Normale Supérieure Technique in Cachan, and this made all the difference. Now, I'm talking about Alain Aspect, talking about Bell, but these prejudices were not so effective concerning them. But concerning other physicists, these prejudices were very effective in blocking their professional career. I want to cite two examples. The first one, it's Clauser. Clauser, for any standard, is one of the best experimental physicists in the United States. He did his PhD in Columbia with Patrick Tadeus, working on microwave measurement. He did his wonderful work with Shimon, translating the theorem to the labs. He further developed Bell's theorem. He replicated experiments. He did the first experiments. He participated in the early debates about quantum optics, but despite all these achievements, Clauser never got a permanent job in the American universities. Okay, I may understand when the time he needed a permanent job in 1972, 1973, it was still the time of the job crisis. You described well in your talk, David, but I also had no doubt that many of the people who could interfere to hire Clauser, they did not believe Clauser was doing good physics. So they were not asking if Clauser was a good physicist. They had doubts if the kind of physics Clauser was doing was good physics. That's the letter we had cited, which is a letter that we know this letter because Bernadette received a letter from the department chairman at San Jose, the University of California, inquiring whether what you have been doing is real physics. So that's how we know. I have other evidence, but I do not have time to go long. We have a second example for me. I have several examples of this. I don't want to my time is run out. But the second I want to say, it's that Hans-Dieter there. He was working on nuclear physics in the late 60s when he wrote a paper which may now be considered a forerunner of the decoherence approach. The paper suggested that the ensemble of a system plus a measurement device cannot be considered a closed system. Thus, approximations are required when you use the Schrödinger equation to describe it. This idea was in other minds at the time, but there was the person who better described it and wrote a paper. But the same idea you can find, for instance, Fock, the Soviet physicist, said something. The system of interest in quantum system, in quantum mechanics, cannot be closed systems. Now, the paper was not accepted by Unova and the Naturwissenschaft. At that time, they worked at Heidelberg under the guidance of the Nobel Prize winner, Jensen, and Jensen decided to ask Rosenfeld's advice on the paper. And this was Rosenfeld's letter to Jensen. It's terrible that they only knew this letter about 6 years ago, when the letter was revealed, because we discovered this letter and we asked the Newsboard archive. Then we gave the letter to them. But they felt that the ambience around him in Heidelberg had completely changed. And it's his reminiscence that he realized at that time when Jensen told him that he should not pursue this line of research, and he realized that all the colleagues at the Heidelberg team knew something about, as if he had done something wrong, but he did not know the letter. And they realized at the time that his academic career was blocked. Anyway, he kept his research. Later, in the 80s, he resumed this subject with a student at IQOQI, but indeed he never got a professorship in the German cases. Now, as I spoke about the quantum dissidents, I needed to say a few words about a problem of generations and change of generations. It's the reason of the question I asked you yesterday. Most of these quantum dissidents were young physicists when they began to work on the foundations. In a time, in 1950s and mid-60s, when the old guard of the founding fathers were retreating for the line of the philosophical battle. Bohr died in 1962 or 63. Paul had died in the late 50s. Right? Heisenberg was alive, but was not engaged in these debates. So there was a real change of generation. We can think about this. However, I think that this idea of this change of generation should be tempered by an information about, by the information that some of these young guys were supported by old physicists who thought there was good physics to be done on this field. I can imagine, for instance, the support Alain Specht had from Claude Cohen-Tanougy, even if following Claude Cohen-Tanougy after the experiments, Bell's experiments, he left the subject to another subject, but he left this to work with Claude Cohen-Tanougy. But Alain Specht also said that during the late 70s, the interaction with Claude Cohen-Tanougy was very important for him in France. I want to say that I did an interview with Anton Zalling a few years ago, and it's clear that Helmut Rausch Rausch was very instrumental in supporting Zeilinger interest in foundation of quantum mechanics, first on neutron interferometer. There is this very famous now 1976 ERIT conference, a conference that Zeilinger was sent because Rausch could not go. And Rausch said in the conference, when he arrived there, the conference was organized by Bell in ERIT, and the subject of the discussion was Bell's theorems, Bell's experiments. And Zeilinger was not aware of the subject because he went to, a young physicist, he went to present this kind of experiments with neutron interferometer and this kind of the minus signs when you rotate the system of 2 pi. And furthermore, Zeilinger was supported by Rausch when he decided to change from neutron interferometer to quantum optics in the late 80s. But I think that the most telling example of somebody from the old generation supporting younger generation, younger physicists, was Shimon, because he was very effective supporting his younger colleagues. Shimoni, who was a student of him, Yanaz, who was also a student of him, Zé, who was not a student of him, I didn't tell this, Zé was strongly supported by Wigner. It was by the hands of Wigner that the paper was eventually published in Foundation of Physics, which had just been founded, and Wigner was on the editorial board. Furthermore, Wigner was very important in this history because different from the old guys like de Broglie and the Einstein, who were against Niels Bohr, so they were critics of what we could call a Copenhagen interpretation. Wigner was completely aligned with the von Neumann's interpretation, or von Neumann's presentation of quantum mechanics. And the clash between Wigner and Rosenfeld in the 60s was also a clash into what we can call, if I use Max Jammer's word, was a clash into the monocracy of the Copenhagen school. I said that in this case, the Copenhagen school, the monocracy broke from the inside. Now, I move for the parts where there are more overlap between my talk and David's talk yesterday, and that's the reason why we go quicker about this field. Not by chance, the 3 books, this slide was prepared, the 2 books and the paper by Flávio Del Santo. Let me know an anecdote. I was in the interaction with Flávio through letters, through David Kaiser, but I've never met him in person. I met him 1.5 months ago. And I was so impressed by this paper that I had no doubt that Flávio was so old as me, or maybe from the older generation, somebody from the generation of Baraka. So I could, it's true that Climério, who is a colleague from Brazil, had told me that I met Flávio, but I did not realize that he was this young guy still doing his PhD and doing physics, and at the same time doing these wonderful papers in. Okay, now what I want to say, these quantum dissidents, they acted, influenced also, not only by the conceptual issues, technical issues, etc., but also they were influenced by some contextual factors. I don't want to speak about the 1950s, but this played a role. Interesting as it may be, the criticism by Soviet physicists and philosophers in the 50s against Niels Bohr thoughts played a role in the sense that this was a kind of support for every Marxist, physicist, Marxist in the world, like David Bohm, like Jean-Pierre Vigier, like Mario Bung, like, it's not Eisenstadt. The guy you cited, the name will come. Eisenstadt is another guy. He is alive. This guy was a Marxist physicist who wrote to defend the hidden. Phaidra. So this was the kind of contextual factor. And this is interesting because if it is true that you had on one side in the 1950s, the apex of Cold War, and you had the Zidanovism in the Soviet Union and McCarthyism in the United States, all of this blocking the free debate of ideas, and you had in the Soviet Union the experience with the prohibition of genetics. In the case of foundations of quantum mechanics, it was different because the kind of criticism the Soviet philosophers and physicists were doing against Niels Bohr's thoughts, it was the kind of criticism that in the West, the same criticism were done by other physicists like Einstein. And this stands in spite of the fact that there were Marxist physicists on both sides of the controversy. Some pro-Bohr, Niels Bohr, like Rosenfeld, like Fock, others opposite to Niels Bohr. Now, in the late, the more interesting part is this, in the late 60s and the 70s, we had this kind of general change in society, cultural change, very related to the escalation of the Vietnam War, but not only this. It was a true change of generation, change of culture. And one of the consequences it was this. In the case of the Italian Physical Society, we have studied, and Flavio Del Santo, and Baracca, and Bedia, there was a true ambience favorable to this kind of research. So this is the picture of the first school dedicated to foundations of quantum mechanics in Varena, 1970. I called this the Woodstock of the quantum dissidents. I don't go into details, but you have here just a few, a few illustrations about the connections the young physicists saw at the time between foundations of quantum mechanics and the cultural changes of the time. I like very much this quotation by Toniette. I graduated with an original thesis on Golgi series, but at that time, nobody cared about it. Then, in the political context of the late 60s, we hoped for a deep change not only in society, but even in the way of doing physics. So, we started from the foundations of quantum mechanics, which I learned from Messiaen. So this is also a picture we both like very much, because this is from the Times. This represents the zeitgeist of the time. So pay attention, please. It's not the physics war. It's the war physicists. So the traditional physicists, and in his mind, you had this kind of question. It was the time, 1969, when Murray-Gell-Mann was blocked to give a talk at the Collège de France because the physics graduate students wanted that he explained why he was supporting the Vietnam War before talking about particle physics. You may have an idea. So it was the year of the strike, research strike at the MIT. Now, I jumped to I have less than, but just a detail. I have here this this interview with Toraldo de Francia, who was the president of the Italian Physical Society at the time. And I like very much because he says something that he saved the Italian Physical Society because the Italian risked being split in two at the time. And he used this kind of denomination I like very much. I had my old teachers who were not fascists, not at all, but certainly reactionary. And the young people who were pro-communist, but too much. And Toraldo de Francia said, we need to do both. We need to do particle research, as has been done, but I'll take care of our needs of the society, which particle don't do, but I could do. It's nice to see that the same context which motivated the Italian Physical Society to dedicate this school to foundations of quantum mechanics, the same decision it was taken to dedicate the 2 years later, the same school, Varena, the prestigious Enrico Fermi School, to history of physics in the 20th century and society, something like that. So we are part of a field here, historians of physics, who we were, in a certain sense, benefited from this kind of changes. I am moving for my final words. Now, on the other side of the Atlantic, similar trends were operating. I wanted just to say that Physics Today and American Journal of Physics, they played a role opening the debate about the interpretations of quantum mechanics. I'm not very interested in the American Journal of Physics, but I am very interested in the case of Physics Today. Because Physics Today, it was at the time on a dispute, reflecting the dispute among American physicists. A part of them wanted the American Physical Society took position against the Vietnam War, and the other majority wanted that the American Physical Society should not take this position. This was a clash among physicists, American physicists, and Physics Today did not publish the letters pressing the community to take position. The editor of the time just took the letters. But at the same year, he took this decision to editorialize a debate about the foundations of quantum mechanics. Then he accepted Bryce DeWitt's idea of publishing a nice paper about quantum mechanics and the reality, and there were a sequence of letters and the articles supporting different views of interpretations on quantum mechanics. One of these letters I like very much because the letter was written by Michael Hamilton, somebody who went to medical physics, use of physics in medicine. And he said there was the very interesting contribution to the quantum mechanics debate in your April issue, and the paper by DeWitt, which triggered them, exemplified the highly complex and subtle ways in which scientific opinion can change. I think that this is a very sociological diagnostic, very precise. And he said, 20 years ago, the Copenhagen line was scientific, and anything else was meaningless, jumbo, and at best mistake. And now, the curious thing is that, as far as I am aware, there was no major finding or theoretical insight that could be held to demolish or supersede this interpretation. This is not very right, because you had theoretical work on the field. But he said, nevertheless, there is now considerable satisfaction with the Copenhagen interpretation and a willingness to regard other point of views. Now, here is where I jump this part, because David talked very well, but I want to, because it's true that I would say that David's books may be read as this, how an important theorem in quantum information was motivated by the work done by this kind of California and the New Age physicists, etc. But it is also true, and this is in your book, that a physicist like John Clause, he was supported by this environment, this social environment, at the same time. So he was part of the physics group, in a time that he had problems to get a job in the American academia. So if you don't want to share his views about New Age and so on, he had a kind of sociability among these physicists. It's not by chance that he said this, that it was only 1976 when the people who work on quantum foundations went out of the closet. Because he was very isolated in the early 70s. He didn't go to the Vienna conference. There was no conference between 1970 and 1976. So the people he was dealing with, it was Shimon, Holt, and these guys. And Clause had this view about quantum mechanics, where he related the spirit of the time against the Vietnam War and his work on quantum foundations. Now, let me jump to my conclusions. Two conclusions, very very short conclusion, because my time is run. What I call the rules of histories. So the quantum dissidents won, in the sense that foundations became a prestige theme in physics. But they had higher expectations. They wanted to expose the limits of quantum mechanics, or to use Clause's words, to check the world, to check quantum mechanics. As late as 1980, John Bell used to say that quantum mechanics is rotten, this famous reference to Hamlet, which was an oblique reference to Niels Bohr. Now, what is the irony of the history is that trying to attack the foundation of quantum mechanics, the quantum dissidents ended up consolidating and developing quantum mechanics itself. And the quantum theory entered the 21st century as vindicated as ever. I think that this is a lesson from history which may lead us to reflect about science, how science reflects. So these guys wanted to check quantum mechanics. In the end of the day, they did not check quantum mechanics. And the second and last conclusion, more explicit, I asked me if there is any lesson from this history or story for physics. I think that the only conclusion, or at least the more important conclusion, is not the details of the conceptual issues, technical issues, philosophical issues. My main conclusion from this history of physics for physics is that we, physicists, we need more tolerance with opposite views when engaging in scientific controversy, particularly when conceptual issues are at stake. Because conceptual issues are like ghosts. They always come back to haunt us if we do not face them. Thank you very much.
Thank you very much for this very interesting talk. So we have now about half an hour for questions for the whole tandem, for both of the morning talks. And
Hi, thank you. That was very interesting. Just in relation to the very end there, I always tell my students when we talk about Bell's theorem, I say, you know, Bell's theorem is probably the most tested, experimental result in scientific history. You know, people are always doing Bell's experiment over and over again. And the reason, I say, it's like, it's in a way it's a test of Einstein's belief in reality and so on. And I say that it's because it really strikes a chord in people and very strong. And I say it's like the fact that, if you have a vampire that's been running around and you're told, that the way you kill a vampire is to stab him with a silver knife at midnight, and so I say even, if the full moon, during a full moon, if the full moon comes and you see the vampire and you stab him, and you bury him, and you're still afraid of him because it's such a fearsome possibility that no matter how many times you kill him, you're always afraid of him.
You need to face it.
I think that's why people keep doing these Bell experiments, because even though they may believe in quantum mechanics, it's still at some very deep level bothers them.
Very good.
Yeah, thank you very much for this insightful talk and for advertisement of my modest work. I have a comment related to what you were saying, which I think is pertinent to this meeting here, and a question. So the comment is about the Varenna School of 1972 in Italy, about the history of physics and society. And I wanted to say that this school laid the foundations for professional engagement of young physicists into the research of history of physics, which led to the foundation of the CISFA, Italian Society for the History of Physics and Astronomy, and eventually for the activation of the curriculum of history of physics within the physics department in Italy at the end of the 70s, as one of the disciplinary sectors of physics within. So the didactics and history of physics became an actual field where you could hire professors in the Italian University in physics department. So meetings of that kind, sensitizing the physicists towards the historical problems, actually this is a nice historical instance where this professionalized some physicists to go into the history of physics and engage with the professional historians and keep these within the. So what we were mentioning yesterday in the panel discussion, how would you feel to have an historian in the physics department after this story happened, and now it's fading. So in Italy, basically there is one single person who's now habilitated to be. To have this role of physicist with the historian affiliation in the physics department, but there are no positions open anymore. I think there are a few retired professors in Rome are left. And the question was instead about the Everett relative state interpretation, where you mentioned that. So you posed the question as is usually not related to a result of the quantum measurement problem, but you can see it like that. And if you could elaborate on this, because in my opinion is the only motivation for the relative state interpretation. Why did you say that this was one can also be seen like this? So what was, in your opinion, the main motivation, if not the solution to the quantum measurement problem?
Okay. First, let me make a comment about the 1972 school, Varenna School on the History of Physics. I can see now, just now, when you remember this, some analogies with the event we are holding today, in the sense that even if the title of the school, which was History of Physics and Society, but you had over there a number of physicists and historians of physics working together. Dirac, the most well-known, but it was not the only. Then, if you want to trace a distant origin for the idea of this conference, this event, you can imagine this kind of collaboration between physicists and among physicists and historians of physics. Now, what I wanted to say about Everett is that nowadays there are different arguments favorable to Everett's interpretation. For instance, I'm not saying which is more important. No doubt that solving the quantum measurement problem in a certain way is one of the attractives, but some people also said that it's necessary for quantum gravitation when you approach cosmology. And David Deutsch said that this was very instrumental when he was thinking about quantum computation. So nowadays you have different reasons to defend or to present the historical context of Everett's interpretation. Now, what I wanted to emphasize is that when Everett wrote his dissertation, you will not find in the dissertation, or maybe you, if you check now, I was so surprised that I want to check Everett's dissertation again, if the term quantum measurements appears in Everett's dissertation. But the motivation was over there, and the motivation was very highlighted when Everett was attacked by people from Copenhagen, particularly Rosenfeld, and when O. Peterson related the criticism from people at Copenhagen. There is a part, I'm not able to remember the exact words, but in this paper, Stefan, who wrote with me, and Fabio Freitas, there is this sentence that Everett answered to Og Peterson, saying that in this country, what we know about quantum mechanics was taught by von Neumann. So I cannot understand what you are saying about this role of and when this role of language and classical concepts, etc. And when I understand, I am more against it. So in this sense, that one strong motivation was the presentation of quantum mechanics done by von Neumann. Just this.
I like the way you said that there was nobody more supportive of the next generation than Abner Shimoni. I thought I would add a piece of evidence to that with an anecdote. So Abner and I certainly had our disagreements about where quantum mechanics should go. For instance, he was rather strongly wedded to the idea that the probabilities in quantum theory are objective probabilities or propensities. And I, on the other hand, wanted to explore a Bayesian route, a subjective understanding of probabilities. And I think it was about in 2010, there was a meeting here in Vienna, and Abner gave a talk, and he recited a large piece of Edward Lear's poem, The Jumblies. And in the poem, there was an emphasis. Abner emphasized a line where it said, we're going to see in a sieve. You know, a sieve is something that you drain water from the vegetables. We're going to see in a sieve. So in other words, we're sinking. And as he read the poem, he looked straight into my eyes. And then after the talk, he came up to me and he said, when I read you're going to see in a sieve, I was thinking about you, Chris. So we had our disagreements. Okay, fast forward to a few years later, or maybe just 2 or 3 years later, we had a conference at Perimeter Institute. I wasn't at Perimeter Institute yet, but there was a conference at Perimeter Institute in honor of Abner. And Abner and I were both taken with the early American pragmatist. Abner he adored Charles Sanders Peirce. And Abner wrote me a letter once saying, you love William James. Chris, you love William James, but I adore Peirce. One of the distinctions between Peirce and James was that Peirce was more for an objective notion of probability and James was more for a subjective. In any case, I was going to give a talk at this meeting titled Peirce, James, and the Quantum Bayesians, and it was going to be about Peirce in honor of Abner. So 2 days before the meeting, I wrote to Abner saying that since I didn't know much about Peirce, I was reading a biography of him. And I said, the more I read of it, the more I become depressed, noting all the similarities between his life and mine. I will see you in 2 days, Chris. And that's all I sent him. I got to the meeting. I didn't get to talk to Abner the first day. But the second day, he came up to me with a very grandfatherly, worried voice. And he said, Chris, are you okay? And I said, yes. He said, I didn't get a chance to talk to you yesterday, but I saw you from the distance, and I saw that you still have your wedding ring on. So your marriage must be okay, but are your children okay? And I said, yes, my children are okay. What is the issue? He said, your life, you said, was so similar to Peirce's. Well, Peirce was a user of drugs. He was a womanizer. He lost all of his money because he lived a flamboyant lifestyle. And so I guess all of these things were going through Abner's head. But particularly, all I meant was that Charles Sanders Peirce was never able to get an academic position. And I, too, had immense trouble getting an academic position because even in my day, I was doing too much foundations, and that excluded me from hundreds of applications. I applied at hundreds of places. I was only accepted at one eventually. So anyway, I said, oh, Abner, all I meant was I can't get an academic position. I can't get an academic. And Abner's reaction was, oh, is that it? Is that all? When I go home, I will talk to my chairman and see if we can find a position for you at my university. So despite all of our differences on the foundations of quantum mechanics, he made a genuine effort to get me into his faculty just because I was young and I needed a job. So I just remember that story of him.
Chris also applied to my school.
I applied to David's school. I applied to the University of Vienna. I applied everywhere.
I had tried for a long time, and I finally got the department to say that a historian and philosopher of quantum mechanics was a respectable physicist, and they were going to hire one. And Chris came along at the opportune time, and they listened to him. And they went ahead and hired a solid-state physicist, because the department was its strongest in solid-state physics. And the next one, I tried to get, and they all agreed, oh, yes, we need a science. But they hired a high-energy physicist. And to this day, they haven't hired anybody in that field. So, and they never will, unless lightning strikes. And so a lot of universities, they feel, well, it would be nice, but especially like at City College, we're having tremendous problems keeping the state funding us and so on. And you don't have that much money, and you don't have that many people you can hire, and you go to your strengths. And that's the way academia has probably always been, but certainly in lean times like these, it is. And it's very hard to hire somebody who's not in one of the predominant, who's not in one of the overhired fields. You know, you can hire a string theorist, even though the evidence for string theory is far worse than anything that's done by the historians of science. And that's the way academia is. Very unfortunate.
Let me make a short comment. I think that it was very appropriate that you emphasize this role of Abner. Everybody here who had the chance to interact with him could have similar stories about how he was interested in supporting people as human being. But I want to say that if you also see some of the roles he played in the debates of quantum foundations, the same pattern you will find. For instance, he organized these epistemological letters, which was a kind of a very informal vehicle for circulating ideas in the 70s, and he was the editor of the epistemological letters. The vehicle was published in Switzerland, but the real editor was him. So he used part of his time for editing a vehicle which was not official vehicle, but he understood that this was important to the debate on foundations of quantum mechanics. And some very important debates on foundations of quantum mechanics in the 70s, you cannot find in any journal except in the epistemological letters, which are now deposited at Pittsburgh University. But I also think that he was, I don't know if he was influenced by Eugene Wigner in this sense, but I would say that Abner and Eugene Wigner had different views about a number of subjects, for instance, politics, Vietnam War, and so on. But towards the debates in science, they were very tuned with each other. I cited this case of Wigner, but if Wigner opened the 1970 Varena School, and his piece over there, I think that it's an example of open mind to when you have a scientific controversy, because he presented 5 or 6 different solutions for the measurement problem. He presented the weakness and the strong points of each one, and in the end, he defended his own view. But before defending his own view, Wigner presented in a very honest, in a very fair manner, all the alternatives which were on the table. And the opposite character, if you compare it with Wigner, it was a physicist from the same generation, Leon Rosenfeld, who was, in this sense, a person who did not help too much to open the intellectual space in physics to the research on foundations of quantum mechanics.
Okay, maybe I take the last question then. Speaking of Leon Rosenfeld, so as it seems he was not a fan of quantum foundations, but still it's not quantum foundation, but he did make one of the earliest contributions to quantum gravity, which he, if I know correctly, later distances himself a little bit from. So I was wondering if this distancing from his early contributions to quantum gravity and his opposing view to quantum foundations is correlated, or is this a different issue?
I can make first an advertisement. We have now a wonderful biography of Rosenfeld, written by Anja Jacobsen, where the evolution of Rosenfeld may be spotted. He was a very complex character in the sense that he himself was engaged in foundation of quantum mechanics. He wrote this paper with Bohr in the 30s. It's true that in that context, it was a different context from the 50s. So it was him and Bohr defending against Landau's and criticism to the possibility of having consistent quantum electrodynamics. And he spent time writing what he saw as the final solution for quantum foundations, which were the epistemological lessons from quantum mechanics, as you said. So you see, he himself, he dedicated to this subject. But I would say that from a certain time, and from my point of view, it was exactly after the World War II, because Rosenfeld was a very committed Marxist. And this kind of debates and battles among Marxists were like a religious battle. So he was against the Soviets, against the Stalin, and he was pro-Bohr. And he simply could not accept the idea that these Soviet physicists or Marxist physicists like Fock, like Bohr, were criticizing Bohr. Then, from that moment on, he acted in a very dogmatic manner. So this Rosenfeld, very dogmatic, very resistant to the open debate. This, for me, it's clear from after the World War II, 1947, 48. For instance, in the biography and also in my book, The Quantum Dissidents, there are evidences that before the appearance of the paper by Bohm, 1952, Rosenfeld, who wrote to Bohr, reporting to Bohr the kind of a battle happening in Soviet Union, in the Soviet Union, on quantum mechanics, and criticizing these guys. And furthermore, he advised the editor of Nature to not publish a paper by Frankel, who was, in a certain sense, critics. There were criticism towards the Niels Bohr thought. So the complexity of Rosenfeld character, you needed to take at least these 2 or 3 parts. He was very uncomfortable with the trends in Soviet Union, philosophical trends, on one hand. He was very convinced that Bohr's thoughts were the epistemological lessons from quantum mechanics, and he tried to sell a story that there was no important question being debated, being investigated by David Bohm, by Hugh Everett. So this is the late Rosenfeld. I think that in a certain sense it's different from the Rosenfeld in the 1930s. But he was a very complex man. And he was a good historian of physics. He supported the initiatives of UNESCO to publish a number. And if you see his collected works, a number of papers are about the history of science, and they are good papers. So he was a physicist and a historian of physics, but a very dogmatic person from the 50s on.
Thank you very much, and thanks again to both of the speakers of the morning, and we will have lunch now until 2. So have a good lunch and see you at 2.